All right, guys. Today we have a special lesson. Today is the last lesson that I'm going to do for circuit analysis. And so once this is finished, we would have gone through all of my notes that I've taken throughout my semester of Intro to Circuit Analysis. And hopefully, as you're taking this course yourself, this lecture series has been able to help you, mechanically work through all of these problems. And hopefully, you're able to learn something, especially from a student's point of view on how to interpret these things and how to actually solve the problems in a simplified way. All right, so let's get right into it. Today we are going to be looking again at power. This time we're going to look at power optimization in a network. And so basically we will have this configuration right here, a circuit with a source network right here, and a load network. So this could be anything. This could be a power grid. It could be your light system in your house. And this source could be the load of the actual source. So I don't know, maybe a complicated battery or something like that, some kind of power grid or whatnot. And essentially, we are going to use the Max Power Transfer Theorem, which we will define the variables as PL average, and that will be the power drawn by the load, where the L stands for the load. So first of all, we are going to have to write an equation that describes this this power that is drawn from this load in terms of these impedances. And from doing that, all we're going to do is take our PL average and we're going to equal that to our full power equation with the power factor. And our max amplitudes are going to be from the voltage load and the current load. We're going to go ahead and turn that into the V squared over R version. And I have written right here V sub L, which is the voltage. This is the voltage difference between ground and the point at which the load system starts. And that is the voltage that we're actually going to use right here. And to get that, we will use a simple voltage divider, something that we learned way back in Unit 1. And so we're going to have the magnitudes of the impedance of L over the magnitudes of ZL plus ZS, and then times the source voltage. And then from there, we're going to recognize that the real part of ZL is equal to RL, which is the resistance portion of the load, and ZL itself is equal to RL squared plus XL squared. Now we're going to go ahead and plug everything in to this equation right here. So PL average is going to equal to 1/2 ZLVS over ZL plus ZS, magnitudes, all of that squared, times RL over, and I forgot the square right here because this is not the power factor. If we had the power factor, then it would just be over ZL. And it would be RL over ZL magnitude squared. And so we can go ahead and cancel these right here. And we are left with 1/2 VS squared times RL over RS plus RL squared plus XS plus XL squared. And that's just because we have right here as ZL and ZS being these guys right here, and then the magnitude, the square root is removed because of this square, and so we can simply just add them up, combine like terms. Okay, and so this is the equation that we will be optimizing. Now I want to look at a few specific cases in which we can optimize things, and specifically 3 specific cases. And so case 1 is going to be changing both XL and RL. Now if we remember, the idea is to optimize this function right here. And to optimize this function right here, if you remember from our calculus days, to find an optimization, you would have to take a derivative, the first derivative test, and you're going to have to make sure that it equals to 0. Now in this first case, we're changing both XL and RL. So what we're going to have to do is consider either side independently. So we are going to perform a partial differentiation of that function PL with respects to XL first, okay? And so a partial is basically just taking all of our variables in the equation, looking specifically at XL and making that vary while holding everything else constant. So that's going to equal to 0. Now after we've differentiated this, let me go ahead and copy this over so that we don't forget what we're actually differentiating or optimizing. So what I like to do is take out all of these constants. These are for sure constants, right? Well, not RL. RL is going to stay where it is. And we're going to take 1/2 VL squared. In this derivation, in this partial, technically we can take out RL because RL is being held constant. So let me just go ahead and do that. Now we're going to take the derivative. Actually, no, I'm gonna go ahead and keep RL up here. So we're going to say use the quotient rule, where we do low times the derivative of the high, and because RL in this case is constant, right, because we're taking the derivative, partial derivative with respect to XL, this whole top part cancels out, the first part cancels out. We're just going to get 0. So you'd have the low derivative, the high, and the high is derivative of the high is just 0 minus, and then now we're going to take the high portion, RL, and take the derivative of the low portion. This is all constant right here in this partial, and so we can just say that's 0, and then we multiply it. We take the chain rule of this right here, so it's going to be 2 times, because we only have one a coefficient of 1 on XL, and it's going to be times XS plus XL. Now, oftentimes today, I'm going to be having our derivation where the bottom is just going to be called d squared, where d is equal to this right here. And the reason why I'm doing that is because I don't want to write this over and over and over again. And it doesn't matter because all of this is equal to 0. So this d squared is going to get canceled in the end. So all of our constants get canceled. And so we're going to be left with 0 is equal to negative r, or negative 2 RL xs plus xl. And luckily, this also is going to get canceled. So we're going to get xs, or xl, because we want to find what xl would be, minus equals negative xs. So essentially, what we're trying to say here is that if we're going to optimize this PL function, we're going to want xl to equal the negative of xs. Now here's the cool thing. When we take our function again, because we found our value of xl that is going to optimize this, we can say that this now is negative xs. So that means that this removes the reactive portion. So we're on our way to optimizing this whole thing. And we get 1/2 Vs squared times RL over Rs plus RL squared. So ideally, when we're optimizing the amount of power, we don't want this reactive noise, okay? Now we're not finished because we can also change RL, okay? So if we're going to also change RL, that means we're going to have to take the partial with respect to RL and equal that to 0, okay? And so here, we're going to take those constants out, and we're going to apply the quotient rule. And this time, we're going to say the derivative of the low times, the low times the derivative of the high, and the derivative of the high is just 1. So we're going to get Rs plus RL squared plus xs plus xl squared times 1. Now here's the thing. I'm going to go ahead and simplify this, but we've already found that in this optimized version of case 1, this right here is just going to be 0, because we know that xs and xl are going to be equal and opposite, okay? So we'll just be left with Rs plus RL squared. We're going to subtract, right, because that's the quotient rule. It's going to be derivative of the low, I don't know why I keep saying that. The low times the derivative of the high minus the high times the derivative of the low. And so here, we're going to say the same thing up here, right? Just about. We're going to say the high is RL times the derivative of the low. Now this time, instead of it being xs and xl, we're going to take the derivative of this portion right here. Okay? So that's going to be 2 times RL plus RS. And then we're going to divide all of that by d squared. And that all equals to 0. Once again, this cancels. But we're left with a little more complicated portion. So we're going to have Rs plus RL squared. I can remove that. Minus 2RL RL plus RS equals 0. We're going to expand this, so it's going to be RS squared plus 2RL RS plus RL squared, and then expand this right here, minus 2RL squared plus, minus 2RL RS is equal to 0. We're going to see that these two cancel out, and we're going to see that we're going to get the negative version right here. And so we're going to say that RS squared minus RL squared is equal to 0. If we take the square root of both sides, we're going to see that RS is equal to RL. So in optimizing for case 1, where we have full control of changing the reactance, so the capacitors and inductors, and changing the resistance, so the resistors in this network, we can see that ideally we would want XL to equal the negative of XS, effectively canceling each other out, and RS equaling RL to gain maximum power. So our final maximum power formula is going to look like this: 1/2 VL squared multiplied by this right here, but with the simplifications. So we'll say RL over, and we already said that this portion is 0, the reactive portion is 0, and then we're just going to plug in RL plus RL squared plus 0, and that's going to equal 1/2 VL squared, and then RL over 4RL squared, and so we effectively get 1/8 VL squared over 1 over RL. Okay? But the idea behind this is this right here. If you can derive these, then you probably have a good solid understanding of case 1. Now case 2. So in case 2, we say that XL is fixed. So we can't change the capacitors and the inductors in this network, but we can change the resistance, which is RL. This time we don't have to work with partials because we know that XL is fixed and we can't change it. So we're just going to use a simple derivative. And that's going to equal 0 for optimization. Once again, we're going to go through our derivation, taking out those constants. We're going to apply the same thing on the top, and we're going to say RL or RS plus RL squared plus XS plus XL squared times 1, because the derivative of the top is just going to be 1, minus our same RL times 2 times RL plus RS, all divided by d squared. And it should be trivial at this point now, but we're going to go ahead and remove these, and then we're going to simplify. I'm going to keep this the same way. I'm not going to expand this right here. I'm just going to say RS squared plus 2RLS, RLRS, plus RL squared. I'm going to just, keep that like that for now. Minus RL, or minus 2RL, RL plus RS. And then I'm going to move this out here, equals 0. We're going to see that these cancel out, and then we're going to see that we're going to get RS squared minus RL squared plus XS plus XL squared is equal to 0. And we want to isolate RL because we have in our favor changing the load. Okay, and so basically we're changing this load right here because we want to find something that is going to resonate with our source. I forgot to mention that before. Like, why are we not changing source? Because the source is something that's given to us. So RL is going to equal RS squared plus XS plus XL squared rooted. Okay, and feel free to plug this back into PL right here, but I will not be doing that because all that matters right now is finding what that value of RL will be if we want to maximize that power. And if we want to actually find what the maximized power is, we just plug in this this equation right here. Okay, let's go ahead and take a look at the final case. Case 3. So case 3 is a purely resistive load. So that means that XL is actually equal to 0. Okay. And once again, we're going to be taking a derivative with respects to RL. And so we're going to equal that to 0. Once again, we're going to go through all of the steps. And I'm just going to go ahead and just quickly go through this. Once again, we're going to take that derivative. We're going to get on the top RS plus RL squared plus XS plus XL squared. And we know that XL in this case is 0. So the load has no reactance, but the source may perhaps have reactance. Minus RL times 2 times RL plus RS. And we're going to divide that by d squared. And that's equal to 0. And once we simplify all of this down, we're going to get 0 is equal to RS squared minus RL squared plus XS squared. And then we get RL is equal to RS squared plus XS squared, like so. And so to optimize this case scenario, where XL is equal to 0, we're going to get RL is equal to the root of RS squared plus XS squared. Okay, nice. Let's go ahead and put this into practice with a few practice problems. Okay, let's take a look at our first problem. So right now we have Sydney here, and Sydney is actually my little sister, and so she's going to be our electrical engineer in this problem. So Sydney's giant house has a network system that needs electricity for her lighting system. She's designing the lighting system from scratch, so she controls what resistors and capacitors and inductors she can use. What is the impedance what is the impedance of her load? What is the impedance she can use if the source network system has an impedance of 100 plus J25? Sorry, that was worded terribly, but basically we are trying to find what would be the impedance of our load if we want to maximize our power. Well, we say that we can vary the RL and XL, so we get to completely determine what that lighting system is going to be. And if that's the case, then we're going to use that RL is equal to RS, right, from our case 1 that we derived. And we know that the R of the network system that's going to be controlling these lights is 100. So we know that RL is going to be 100. We also know that XL is equal to negative XS, and therefore the XL is going to equal to the negative of this reactance right here, which is 25. So negative 25. So the impedance is simply ZL is equal to 100 minus J25. Super easy, isn't it? Now, what is the max power that can be drawn? So what actually is that max power? Well, we can just say PL, P average L, the average PL, equals 1/2 VS squared times RL over RS plus RL squared plus xs plus xl squared. That is equal to 1/2, and our voltage right here, this is actually wrong. This is supposed to be an AC power source. That is, that looks like this. And so our VM is 120. So 120 squared times 100 divided by 100 plus 100 squared plus 0, because 25 minus 25 is just 0. And correct my math if I'm wrong, but once I've already pre-calculated this, but PL average is going to be 18 watts. So Sydney's lighting system draws 18 watts of power. Now let's go ahead and move on to the last problem. Okay, let's take a look at our last problem. I actually had to do a few revisions on this. I did this at the airport and I just realized there were so many mistakes, but I think we're good now. So here it looks like I've been hired to help improve the Dallas power grid. The city power regulator is shown down below. The city asked him to fix up the power grid's receiver, but the city only wants him to use resistance. So that sounds like a specific case of ours. The capacitance of the grid receiver is 5 microfarads. What is the max resistance Alex can add to the receiver to achieve max power transfer? I think that this makes it a little unclear right here. Wants him to only use resistance, given the fact that there already is a reactance, a capacitor that's been attached to this. So essentially we're just trying to say that with a fixed XL, what is the RL that we can add that will make the max power transfer? Okay, so this right here is our network, okay, our source. This is the power grid right there, and this right here is the receiver. Okay, so we want to make sure that there's max power transfer between them. Now, as we've seen in in a lot of this unit, when we're given a configuration like this, it's best to just go ahead and simplify it down. And so I'm going to quickly go through the simplification. I'm going to speed it up. Okay, so we have the individual components found. ZC1 is negative J500, ZC2 is negative J312.5, and ZL is J800. Now, the C2 is in parallel with L, so we're going to go ahead and solve for ZLC2. And we're going to get approximately negative J512.82. And now we can say that this is in series with this and is series with this. So our Z total is simply just going to add all of those things together, and we're going to get our 1K ohms, and we're going to add them up to the J, is it negative J 500 minus J 512.82, which is just equal to 1000 minus J 1012. Like that. Okay. Now, before we move on, we're actually going to have to figure out this impedance. This impedance also. So I guess we can just call it ZC load, because if I put CL, that's going to look weird. So that's just going to be 1 over J times 40 times 5e to the negative 6. That's going to be negative J 5000. Okay. And now we're going to use our optimization rule for, we know that the RL is changing, and we know that we have an XL, so we're going to use RL is equal to RS squared plus XS plus XL squared rooted And so it's just a simple plug and chug. 100 squared plus negative 1012.82 minus 5000 squared. And it appears to be, after simplifying this down, we get RL is equal to 6.095 kilo ohms. So this resistor right here is going to be about 6,000 ohms. So that works out. And obviously these are not real numbers. I don't think that the city would have such low of a resistance. I think a lot of things are going to die in that case, but that's the answer for this problem. And so those are just two applications of maximizing power. Maybe not realistic, but maybe with different numbers, they would be. All right, guys. Thank you so much for watching this video, and thank you for, hopefully, if you stuck through the entire circuits analysis curriculum or whatever this is, lecture series, archive, you enjoyed it, you learned something. Hopefully you identified some mistakes that you, or anything like that, because then that means I know that you know how to do this stuff, and hopefully whoever's teaching you or whatever will be able to see that you're trying on this. It's not too difficult. It does have a level of math and stuff that you need to know, and intuition, but that's stuff that we will build as we continue our journey as engineering students, STEM students, or just somebody who's a hobbyist or just wants to know what's going on. But yeah, I hope that I will make a few more tutorial videos. Hopefully they'll be better than this lecture series, and hopefully they'll evolve into something better. But yeah, I hope this helped first and foremost, and yeah.